This is the 17th video in a series devoted to complex analysis. And today we're going to look at power series of complex valued functions. So let's recall a definition. So a power series centered at a complex number z0 is a series of the form the sum as n goes from 0 to infinity of an times z minus z0 to the n, where these coefficients a sub n are complex numbers. Now notice we can do a quick change of variables where we switch out z for maybe z plus z0, and we can transform this back to being centered at 0. So what that really means is that we only really need to prove results for power series centered at 0, and then apply a transformation to get those results about power series centered at z0. So most of the time when we're proving results, we'll do these things centered at 0. Okay, so let's look at this first theorem, which is something that's probably similar to something you saw in a real analysis class. And it says, for any power series, which is given by the sum as n goes from 0 to infinity of an z to the n, there is a capital R which is bigger than or equal to 0. It may be equal to 0, but it could also be positive infinity, such that for all complex numbers z where the modulus of z is less than r, the series absolutely converges. And then for all complex numbers z where the modulus of z is greater than r, it diverges. And just FYI, this r is called the radius of convergence, just like from a calculus or a real analysis class. So here's a picture of what's going on here. So we've got our complex plane, and here I've got a circle of radius capital R in yellow. And so inside this circle is all complex numbers whose modulus is less than r, and in here the series absolutely converges. And then outside of this circle the series diverges. But on the circle itself, it's a bit unclear. Sometimes it might converge and sometimes it might diverge, depending on exactly where on the circle we are. So let's do the proof of this theorem before we look at like a bunch of examples and stuff like that. Okay, so let's note first, to get started, that the sum as n goes from 0 to infinity of an times 0 to the n always converges. In fact, it absolutely converges. Well, why is that? Well, it's really just the sum of 0 over and over and over again, so there's not much to do there. So that means that we at least have this case of convergence for r equals 0. Okay, so the next thing that we want to do is suppose we have some r bigger than 0 such that the sum as n goes from 0 to infinity of the modulus of a sub n times r to the n converges. So if no such r exists, then that means our capital R down here is just equal to 0, and really we only converge at the origin. So maybe that's not a super interesting case. And now let's note that if we have a z in the complex numbers where the modulus of z is equal to r, then we know that the sum as n goes from 0 to infinity of a sub n z to the n, where we take the modulus of the whole thing, converges. So why is that? Well, that's because that's equal to this thing up here, which we started off assuming converges. But if this sum of the modulus of these terms converge, that means if we take the modulus out, it absolutely converges. That's the definition of absolute convergence. So we have the sum as n goes from 0 to infinity of an z to the n absolutely converges. And then maybe also, if the modulus of z is less than r, we know that the sum as n goes from 0 to infinity of a sub n z to the n also absolutely converges. And that's by the comparison test. So we can take the modulus of this but each term from the modulus of this is less than each term from the modulus of this. So that means the sum where we take the modulus here converges, but that means this thing absolutely converges. And that's happening for all z within this radius r. So that means that we're setting up this disk here where this thing converges. So now what we'd like to do is push this disk, this little r, as large as we can. And we'll do that by taking the supremum. So let's take capital R, like I said, to be equal to the supremum of all little r, such that the sum as n goes from 0 to infinity of the modulus of an, r to the n, converges. And now from this definition of capital R, it's pretty easy to see that our series converges when the modulus of z is less than r, and it diverges when the modulus of z is bigger than r. But again, we don't have any information what happens on that radius in this case. That's because we're taking a supremum, not a maximum. Okay, so that's the end of this proof. So let's maybe get rid of this and look at some examples. So here's some examples, some of which are probably familiar from a calculus class, but have been pushed into the complex plane. So the first one is this sum as n goes from 0 to infinity of z to the n. So this is the geometric series. So it has a radius of convergence of 1. And in fact, it converges inside this disk with radius 1, but it diverges everywhere along the boundary. And so you can check that by the test for divergence. And notice if you take something on the boundary and raise it to the nth power, that thing will never approach 0. And by the test for divergence, that means it diverges on the boundary. Okay, so let's look at this next one. It's somewhat related to a harmonic series. So the radius is 1 again. We have the sum as n goes from 1 to infinity of z to the n over n. And this thing converges, well, everywhere in the disk and everywhere along the boundary except this point right here, z equals 1. Notice if we plug z equals 1 in here, we get the harmonic series, which is well known to diverge. If we plug z equals minus 1 in here, that's called the alternating harmonic series. And in calculus, you find the sum of that. So that converges. But in fact, it also converges at every other point along the boundary, except for that really bad point, which is z equals 1. We're not going to check this right now. In fact, you need a few more tools to check this, which we haven't introduced yet. Okay, now what about this? The sum as n goes from 1 to infinity of z to the n over n squared. So again, the radius is 1, but this converges everywhere along the boundary. Notice if n equals 1, we get the famous sum of reciprocals of squares, which that sums to pi squared over 6 kind of famously. Now we've got a particularly poorly behaved power series. The sum as n goes from 0 to infinity of n factorial z to the n. This only converges at the origin, and in that case you get 0. So the radius of convergence is 0. Next we have the sum as n goes from 0 to infinity of z to the n over n factorial. That's related to the exponential function. That thing converges everywhere, so the radius of convergence is infinity. Okay, so now that we've got this, let's look at our next result. So our next result has to do with whether or not the function defined by a power series is analytic. And it turns out it is in the right region. So let's suppose that f of z equals our power series, the sum as n goes from 0 to infinity of a n z to the n. And also we'll suppose it has a radius of convergence of r. Then that means that f is analytic on the set of all z where the modulus of z is less than r. And this proof is actually pretty quick based off of some stuff we did in a previous video. So let's look at it. So let's define the following sequence of functions. So that sequence of functions will be defined as follows. So fn of z is the sum as m goes from 0 to n of an, or I should say am z to the m. So this is the nth partial sum of our infinite series up here. So the next thing that we want to notice is that each Fn is analytic everywhere on all of C, and that's because it's a polynomial. And then furthermore, based on the way that f is defined, we have Fn converges to f uniformly on the region where the modulus of z is less than r. But let's recall that if we have uniform convergence of a sequence of functions, and each of those functions is analytic, then the limiting function is also analytic. And it was particularly important to have uniform convergence, not pointwise convergence. But again, like I said, this uniform convergence comes from the fact that we're defining our function as this power series in the first place. Okay, great. So again, since this f is the limit, the uniform limit of analytic functions, that means that it is analytic. So is analytic. Well, it's really only analytic on the region where it converges, but it doesn't really exist outside of that region. So is analytic on the region where the modulus of z is less than r. And that finishes this proof. Okay, so let's look at a couple of examples. So for our example, we'll start with this geometric series we had before. The sum as n goes from 0 to infinity of z to the n, which as we discussed is analytic on the open unit disk. So that's going to be all z where the modulus of z is less than 1. Furthermore, by the standard rule for the sum of a geometric series, we know that this sums up to the function 1 over 1 minus z. So that tells us that this 1 over 1 minus z is analytic for all z where the modulus of z is less than 1. You might say, well, this thing is analytic a lot of other places. In fact, it's analytic everywhere except at 1. But that's not really what this is saying. This is saying how big of a radius can you get from the origin and still maintain an analytic function inside of that radius. And if we gradually extend our radius from the origin until we hit a point where this is not analytic, we stop when z is equal to 1. And that gives us this disk right here that we discussed on the previous board. Now I want to use this to construct two more functions that are analytic in this region. And I'll do that using standard tricks that you would use in like a calculus class to build old series from new series from old series. So the first thing that I'll do is take the antiderivative with respect to z. But we should be careful about that because the antiderivative here will be a logarithm which has a principal branch. And so we'll take the principal branch. So this will be minus the logarithm of 1 minus z equals the sum as n goes from 0 up to infinity of z to the n plus 1 over n plus 1. And you might say, well, how do we know we took the principal branch there? Well, we just make sure that a certain value of z matches on both sides. If we plug in z equals 0 to this left-hand side, then we get the principal branch of the log evaluated at 1, which is equal to 0. But if we plug z equals 0 into the right-hand side, well, then we just have a sum of a bunch of zeros. So this thing matches values at z equals 0. So we're good to go here. Okay, then what we'll do on the right-hand side here is take the derivative. So recall that we had derivatives with respect to z and z bar. We'll use the derivative with respect to z. And that'll give us 1 over 1 minus z quantity squared equals this sum as n goes from 0 up to infinity of n times z to the n minus 1. So let's notice we don't really need the 0th term in there because the derivative of the 0th term is 0. So that gives us another function that is analytic for this region as well. Okay, so now that we've done that, I want to recall a couple of results from calculus or real analysis before we look at how to find coefficients when we have an expansion of a general function. So before we jump into finding the coefficients of a series expansion for a given function, let's recall the following two tests for calculating the radius of convergence, which you probably saw these before in like an analysis or a calculus class. So let's just recall we can calculate the radius of convergence capital R of the power series defined by the sum as n goes from 0 to infinity of a n z to the n by this thing called the ratio test, capital R, which is the limit as n goes to infinity of the modulus of a n divided by a n plus 1. Next is the root test, which is capital R equals the limit as n approaches infinity of 1 over the nth root of the modulus of a n. So these are both really nice tests for calculating this radius of convergence. Okay, so now let's look at finding the coefficients. Let's suppose that f of z can be expanded as the sum as n goes from 0 to infinity of a n z minus z naught to the n, and that expansion is analytic on this disk centered at z naught with radius r. So that's an open disk. So now what we'd like to do is form some sort of formula that will allow us to calculate these coefficients if we are given the function. And we can calculate the relation between these two fairly easily. So what we'll start by doing is maybe just noticing that if we evaluate this thing at f of z naught, then this sum collapses to a single term. And that's because if you plug z naught into here, you get 0 everywhere except the very first term. And in that case, you'll have a sub 0, and that's it. And so we want to generalize this idea to write these other coefficients in terms of values of the function, and we can do that by taking derivatives. So let's take the mth derivative of z and see what happens. So let's see, the mth derivative of z will be the sum as n goes from 0 to infinity of n times n minus 1 times n minus 2 all the way down to n minus m plus 1, and then an times z minus z naught to the n minus m. So we have a product of m terms here, and we had to subtract m from the exponent there because, again, we're taking the mth derivative. Okay, good. Another thing that I'd like to notice is that this sum really starts at m, and that's because the 0th term cancels out because of this. The n equals 1 term cancels because of this. And in fact, everything up to the nth term cancels because of those coefficients. So I can really change this to starting at n equals m. Next up, we'll extract the mth term, but notice the mth term will have a product m times m minus 1 times m minus 2 all the way down to 1. That's also known as m factorial. And then we'll have am, z minus z naught to the m minus m, but that's just the number 1. Okay, so that is the n equals m term. But then let's see what we get for the n equals m plus 1 and higher term. All of those have a factor of z minus z naught in them. So I can factor out a z minus z naught. And then we'll have this sum as n goes from m plus 1 to infinity of all of this stuff. So n minus 1 all the way down to n minus m plus 1, a sub m, and then we have z minus z naught to the n minus m minus 1 because we took this out. So that's looking good. But notice if we evaluate this at z naught, we cancel out all of the rest of this stuff, this infinite tail, if you will. And that tells us that the mth derivative evaluated at z naught is just m factorial times a sub m. But that's good news because we can solve for a sub m in terms of something having to do with the function here. So that means a sub m equals the mth derivative evaluated at z naught divided by m factorial, which is the well-known formula that you learned when learning about Taylor series for the first time. But let's also recall that since we're in complex analysis, we have something called the Cauchy integral formula. So we can, in fact, apply the Cauchy integral formula to write this a little bit differently. So let's see how we could do that. So I'll just recall that the nth derivative can be written in terms of a certain integral. You can look that Cauchy integral formula up if you want to, but what we end up with is a sub m is equal to 1 over 2 pi I And then the integral over the circle w minus z naught equals r, little r, where that little r is any number which is less than that big R. And then we have f of w over w minus z naught, let's see, to the m plus first power dw. So that's what we get there. And like I said, this R is anything which is less than R. So just to reiterate what we have here, we've got two formulas for our coefficients of a series expansion for a function. One, which is like something you might see in real analysis, and then this special one down here, which only works for analytic functions in the complex plane. Okay, now let's get rid of this and we'll recall a bunch of examples of functions. So here's some common functions. So the first couple we'll look at will have a radius of convergence of infinity. So we have the exponential function e to the z can be expanded as the sum as n goes from 0 to infinity, z to the n over n factorial. Then we have sine and cosine. So sine is the sum as n goes from 0 to infinity of minus 1 to the n over 2n plus 1 factorial, and then z to the 2n plus 1. Cosine is pretty similar here, except we've got 2n, an even number factorial in the denominator, and z to the 2n. This really hammers home the fact that sine is an odd function. It only has odd powers of z, whereas cosine is an even function. It only has even powers of z. So next we've got some that have a radius of convergence of 1. All the ones we looked at previously also have a radius of convergence of 1, so you can think of those as being on this list as well. The first is the principal branch of the arctan, and that will be the arctan of z, the inverse tangent of z, which is the sum as n goes from 0 to infinity of minus 1 to the n, z to the n plus 1 over 2n plus 1. And I'd like to point out that this is the principal branch in that we have arctan of 0 equals 0. And that's how we get those two series to match. Then next we've got a binomial expansion. So 1 plus z to the alpha is the sum as n goes from 0 to infinity of alpha choose n z to the n. So I think we looked at complex valued binomial coefficients earlier. And here, for the radius of convergence to be 1 and not infinite, we need alpha to be on the set C, where we've removed the non-negative integers. So we've removed 0, 1, 2, 3, so on and so forth. And we do that because in those cases, this is just a polynomial. And polynomials clearly have an infinite radius of convergence. Furthermore, for values of alpha which aren't integers, this thing has multiple branches, and so we'll take the branch where 1 to the alpha is equal to 1. Okay, so I'll finish off giving you guys some warm-up problems. So I'll leave you with two warm-up problems, one of which has two parts. So the first is to find the series expansion of the principal branch centered at the origin, z equals 0, of the function f of z equals the square root of 1 plus z squared and the arc sine of z, where, like I said, those are both principal branches. The next is to expand the function, which is the principal branch of log 3 minus iz, as a power series centered at z equals 2i, and then describe the region of convergence. Okay, that's a good place to stop.